Dear trainees, in previous class, that is coal to electricity, we had seen the process in brief, how the heat of coal combustion is used to convert water into steam. This steam, which is generated by absorbing the heat liberated from the coal, passes through turbine, and this turbine get rotated, and in turn the generator, which is coupled in series with the turbine, also rotates, and finally we are getting electricity produced. Now in present discussion, we will learn some fundamental concepts of thermodynamics, how steam is generated, the properties of steam, and the modified Rankine cycle and its analysis, over which the thermal power plant works. So before moving ahead, definitely we have to know that what is thermodynamics. Basically, thermodynamics is science of energy. There are many forms of energy, that is heat energy, work energy, electrical energy, kinetic energy, potential energy, and many of them you are aware with. But basically in thermodynamics, we talk about only two forms of energy, that is heat energy, work energy, and their mutual conversion. You all must be knowing that law of conservation of energy, which tells that energy is conserved. Energy can't be created and destroyed, only it can change its form. It means that heat can be converted into work, or work can be converted into heat. But overall energy will be conserved. So there are three energy states. One is unstable, second one is stable, and system is in lowest energy state, and metastable is that state where a slight disturbance will change its state and it will attain a new final stable condition. Now we will see that what is a thermodynamic system, what is surrounding, and what is its boundary. So system can be defined as a quantity or matter or a region in space chosen for a study. As for the example, in a thermal power plant, in totality thermal power plant we are discussing, it is a system, but a thermal power plant consists of a number of equipments as boiler, turbine, condenser, generator. So suppose we are doing the analysis of turbine, or we are putting our focus over the turbine only. So for this type of case, our turbine will become a system. Suppose exclusively we have to analyze the performance of boiler or what is happening with the boiler, then boiler will be supposed to be our system. So system, it is our point of view which we select for the purpose of study. Then the mass or region outside of the system will constitute its surrounding, and boundary, it may be real or imaginary, that separates the system from surrounding. Now the concept of state, thermodynamic equilibrium, and thermodynamic process is very important to understand. State can be defined as a set of properties that describes the condition of a thermodynamic system. Here we are talking about the thermodynamic system. So some properties are mass, temperature, volume, entropy, enthalpy, and etc. Then second thing that comes is thermodynamic equilibrium. Any system will be called under thermodynamic equilibrium when it maintains simultaneously thermal equilibrium, mechanical equilibrium, phase equilibrium, and chemical equilibrium. It means there is no thermal temperature change, there is no unbalanced mechanical force in the system. It is in a single phase and no chemical reactions are taking place. So if altogether these four equilibrium exist, then we can say that our system is under thermodynamic equilibrium condition. This figure shows the state of a thermodynamic system when its temperature was 20 degrees centigrade, mass was 2 kg, and volume was 1.5 meter cube. Due to some, or you can say that this particular state has changed from 1 to 2 because of undergoing some process. Now second state, which is described by new set of parameters, that mass, because there is conservation of mass, there is no mass going out, so it will remain constant. Temperature is same and volume has increased from 1.5 meter cube to 2.5 meter cube. So this is a new state of the thermodynamic system. So thermodynamic system may go through number of states, state 1, 2, 3, 4, and if we draw locus of these state points, then that will be called as the path through which a thermodynamic system is going through. You must be aware with some processes, that is isothermal process, isochoric process, isobaric process, isentropic process. So this word iso is used to designate a process for which a particular property remains constant. The representation of these processes in a Cartesian coordinate system is just like representing a point in XY plane. So each state you can assume as a point. You know that in Cartesian coordinate system, to represent a point, we require minimum two inputs, that is x coordinate and y coordinate. Similarly, for representing a thermodynamic system, a thermodynamic state in a thermodynamic plane, where on y-axis and x-axis we can select our thermodynamic properties, we will require two inputs in form of thermodynamic properties. As in the present case, we are talking about isobaric process. This is the process where pressure remains constant and change in pressure will be equal to 0. So this isobaric process can be represented by a straight line which is parallel to the axis, which represents specific volume. It is similar as in coordinate geometry. A line parallel to x axis will be represented by y equal to constant. Similarly, for isochoric process, in isochoric process, or that is also known as isometric process, the volume remains constant. So it will be represented by a line which is parallel to the axis representing the pressure value. Isothermal process is the process where the temperature remains constant. For this, we are selecting temperature as a variable on y-axis, and on x-axis we can take anything like specific volume, entropy, and other parameters. So in nutshell, we can say that isobaric process is a process where pressure remains constant. Isothermal process is the process where temperature remains constant. Isochoric process is the process where volume remains constant, and isentropic process is the process where entropy remains constant. I would not like to go much in detail for entropy, but however, entropy is defined as it is the measurement of the randomness of the system. Thermodynamic processes are basically classified as cyclic process, reversible process, irreversible process. Cyclic process is that process in which a system is starting from one state condition after passing through different processes, again return back to its initial state. Then we can say that system has undergone a cyclic process. Now, a reversible process, it is a thermodynamic process. If the process can return back in such a way that both the system and the surrounding return to their original states with no other change anywhere else in the universe. Or you can understand as both system and surroundings are returned to their initial state at the end of reverse process. Irreversible process is that process that cannot return both the system and surrounding to their initial condition. The reversible process is an ideal process, practically which never occurs, while the irreversible process is the natural process and that is commonly found in nature. The generation of steam and conversion of steam into again condensate or liquid form, or rather you can say from liquid to the vapor conversion and again from vapor to liquid conversion of water is a reversible process. It can be assumed as a reversible process. However, suppose we are burning a paper, the paper will become ash. So again, ash can't be turned back into form of paper. So that can be treated as an irreversible process. And irreversibility in the process comes because of the existence of friction in the system. Adiabatic process is that process where there is no exchange of heat between system and surrounding. Isentropic process is also an adiabatic process. Apart from no heat exchange, the entropy of the system also remains constant. Polytropic process is that process which obeys the law PV to the power n equal to constant, and in this process heat transfer is allowed. Throttling process is a process where in which there is no change in enthalpy from state 1 to 2 and no work is done. The unit of temperature is degree Celsius, Kelvin, Fahrenheit, Rankine. Mostly in power plants, generally temperature units what we are seeing is degree Celsius or Kelvin, and their conversion is given here in these relations, by these relations. Then common units of energy, that is calorie and joules. Watt is the unit of power, and its unit is joules per second. Kilowatt hour can be defined as energy transferred if a power of 1000 watts run for an hour. The conversion of kilowatt hour into joules is given by this relation, that is 1 kilowatt hour is equal to 3.6 million joules. Heat transfer in a system takes place because of existence of temperature gradient. We can also say that heat is thermal energy that is in transit. Touching objects causes an exchange of thermal energy. In natural way, energy flows from hotter to colder body, and if there is no flow of thermal energy, then objects will be in thermal equilibrium. There are three modes of heat transfer. One is conduction, one is convection, and third one is radiation. Conduction mainly takes place in solids. Convection takes place in fluid or at the boundary of solid and fluid. Radiation does not require any media. We had seen in practical way that when iron rod is brought in contact to a heat source at one end, after span of time, when a steady state is achieved, the other end also get heated up. This is because of heat transfer through conduction. There are two theories for defining conduction. One theory tells that the mobile or free electrons are basically the carrier of heat, and this heat is being transferred through these free electrons. And second theory tells that heat transfer is because of the vibration of atoms in their lattice. So, as we know that electricity is also conducted because of the motion of free electrons. That's why a good conductor of electricity will also be the good conductor of heat, because in both the cases the free electrons are playing major role. Second mode of heat transfer is convection. This in daily life we have seen. The air once get heated up, its density decreases and it moves in upward direction, and it pushes the cold, heavier air having more density to the downward. Because of this, a convective current forms in the system. There are two types of convection. One is called as natural convection, and second one is called as forced convection. The natural convection takes place because of the density difference, and forced convection required some external media for the transportation of fluid. In radiation or radiative heat transfer, the heat transfer takes place by electromagnetic waves. At higher temperature, more radiation takes place. The understanding of the mode of heat transfer is very important, because in boiler or in thermal power plants, basically in boiler, when the heat from the combustion of coal is transferred to the water that is moving in the water valve, so first the heat is transferred through the water valve thickness through conduction, then at the inner wall surface and the water interface, the heat transfer is by convection, and throughout the fluid heat transfer is by convection. Similarly, in first pass, that is radiant pass of the furnace, most of the heat transfer is because of the radiation. Radiation does not require any media. And second pass, mostly where the LTSH and economizer is there, the heat transfer is because of the convection. See the different laws of thermodynamics, and basically we will focus over zeroth law, first law, second law, and its application. So we will start first with zeroth law of thermodynamics. It tells that if there are three bodies, body A is in thermal equilibrium with body B is in thermal equilibrium with body C, then body A will be also in thermal equilibrium with C, and all these three bodies will be in thermal equilibrium with each other. Zeroth law of thermodynamics also a basis for our temperature measurements. The temperature measurement by thermometer is an application of zeroth law. The first law of thermodynamics, which is also known as law of conservation of energy, it tells that heat and work are mutually convertible and they are equivalent. Energy is conserved, only it changes its form, and the change of energy of system is independent of the path taken. But actually heat and work are not equivalent exactly. When we are giving or when that heat is converted into work, before the start of the conversion, some amount of energy is stored in the system as in form of internal energy. Enthalpy is another important thermodynamic parameter. It is defined as the total energy of a thermodynamic system. Enthalpy is given by the expression H equal to U plus PV, where U is the internal energy and PV is the work energy. So from here we can see that total energy of the system is internal energy plus work energy. There were certain unexplained things from the first law due to which the second law was developed or it brought in picture. The first thing which first law tells that heat and work are equivalent, but exactly it is not like that. So second law gives the concept of quality of energy. Quantitatively energy is conserved, but qualitatively it is not like that. Heat and work are of not the same quality. One is more precious, that is work, that is finished form of energy. Second law also gives the concept of high grade energy and low grade energy. Heat is supposed to be the low grade energy, and work and electrical energy, they are categorized as the high grade energy. So the complete conversion of low grade energy into high grade energy is not possible. This quality concept we can understand by a simple example, that 1 kg of cotton and 1 kg of gold, by quantity they are equivalent, but when the question of its cost comes in the picture or the quality comes in picture, so gold is having more worth in comparison with the cotton. Similarly, the work has more worth in comparison with the heat. So a number of heat units are required to generate 1 unit of finished form of energy. Here that can be work. Second thing, first law never tells about the direction of flow of energy. And third thing is, which second law gives, it gives the concept of source and sink. It means that there should be some source from where that our system takes heat. Some portion of that is being converted into useful work and the remaining is exhausted in the sink. So the process must satisfy the first law in order to occur. Satisfying the first law alone does not ensure that process will take place. Second law is useful in understanding that it gives means for predicting the direction of process, establishing conditions for equilibrium, determining the best theoretical performance of cycles, engines, and other devices. So thermal power plant is also a type of heat engine. It also tells about that naturally energy flows from high gradient to low gradient. But if the reverse we have to do, some external work has to be done over the system. So those were what we discussed earlier, were basic thermodynamic concepts, and one must have the fair idea about those concepts to understand the things what we are going to discuss here. For this you can refer any good thermodynamics book to just clear more concepts and develop a better understanding of the subject. As by now we are aware that the motive force for rotating the turbine comes from steam. So here we will see that how steam is generated, types of steam, some critical parameters. Steam is generated from water. Water is also called pure substance. So definition of pure substance is that it is a matter which has a homogeneous and invariable chemical composition and may exist in more than one phase. So you know that water exists in three phases: solid, liquid, gas, and in both the phases, or all the three phases, its chemical composition remains same, that is H2O. Some other examples are mixture of some other examples of pure substances are mixture of liquid water and water vapor, carbon dioxide, nitrogen, mixture of gases such as air, as long as there is no change in phase. Now we will see that how pure substances changes its phase. So already we had discussed that especially for the water, it exists in three phases: solid, liquid, gas. So there are many practical situations where two phases of a pure substance coexist in equilibrium. As example, water exists as a mixture of liquid and vapor in the boiler drum. Boiler drum's purpose is to separate the vapor water, or rather you can say the water in vapor phase and water in liquid phase. So solids are having stronger intermolecular bond, liquids are having intermediate intermolecular bond, means the binding energy between solid molecules are more. Liquids are having, comparatively to solid, a lesser intermolecular binding energy, and gas are having very weak intermolecular bond, so that's why you can see that they can move. So we can say that gas molecules are having more degree of freedom in comparison with the solid and liquid. We will learn that how water changes its phase from liquid to vapor, or how that steam is generated. So here we are taking the case that in a vessel, water is at 20 degrees centigrade and it is under a constant pressure of 1 atmosphere pressure. So all of us know that at 1 atmospheric pressure, water boils at 100 degrees centigrade. So here we will see exactly when we start heating the water which is at 20 degrees centigrade, what happens, how the things takes shape, that we'll try to understand. So initially, when water at 20 degrees centigrade under 1 atmospheric pressure is heated, its temperature from 20 degrees centigrade liquid to 100 degrees centigrade liquid becomes. This we can see in this diagram that from state 1 it reaches to state 2 at 100 degrees centigrade. So this point 2 is known as saturation point of liquid. You can see here there is a boundary. So this line is saturated liquid line. This is your saturated vapor line. This is subcooled zone. This is superheated zone. So when water is heated from point 1 at 20 degrees centigrade, first it reaches to its saturation temperature of 100 degrees centigrade at 1 atmospheric pressure, and the phase remains liquid itself. So this process of 1 to 2 is known as sensible heating. Sensible heating means the phase remains same and the temperature changes. So you can see from here that at point 1 the temperature was 20 degrees centigrade. At point 2 it has become 100 degrees centigrade, means all the molecules of liquid water has attained a temperature of 100 degrees centigrade, that is saturation point at 1 atmospheric pressure. Now you can see the state 3, which is represented here. After reaching the water sample at point 2, that is at saturated liquid condition, further if we are heating the sample, then in between this point 3 is there, so water now start changing its phase from liquid to vapor. So point 3 is some intermediate position where you can see this in between zone. This in between zone is known as wet zone. So this is total liquid, this is saturated liquid line, this is saturated vapor line, this is superheated zone, and in between this zone is known as wet zone. So the condition of or the state of water at point 3 is the mixed phase. It is partial liquid and partial vapor. So this is also seen here that some portion of water is still existing and some portion of the water has been converted into vapor. So liquid water has been converted into vapor. Now when we further heat our sample, so this point, the water from point 3, it reaches to point 4 condition. It means all the liquid portion of the water sample is now converted into vapor, and at point 4, because this falls over the line that is known as saturated vapor line, so the condition of our sample at point 4 will be, that is dry saturated vapor or dry saturated steam. Now water at that sample, the substance at 4 is in vapor condition. So now further when we are applying heat, this can be shown from here. So already all water molecules has changed its phase from liquid to vapor while reaching to 2.4. Now further heating, it will again start its sensible heating and its temperature increases and phase remains same, that is vapor. So at point 5, the steam or vapor is in superheated condition. And you can, one more thing you can observe, that as we are moving ahead, the enthalpy or the total energy of the substance is also increasing, or rather you can say the total heat content of the superheated steam will be more in comparison with the dry saturated steam, and its work developing capacity will be also quite high in comparison with the dry saturated steam. Now some properties are that we can see from this table. The temperature corresponding to saturation pressure. So at 0.26 kilopascals, the saturation temperature is -10 degrees centigrade. Similarly, when we are moving ahead, the saturation pressure is increasing, our saturation temperature is also increasing, and finally at 101.4 kilopascals, that is atmospheric pressure, the saturation temperature becomes 100, that is also known as boiling point of water. So here you can see, as our pressure is increasing, saturation pressure is increasing, this temperature, saturation temperature is also increasing. And over this diagram, this point is known as critical point, where this saturated liquid line and saturated vapor line joins together. You can see here in between, this is saturated liquid vapor region or wet zone, and the meaning of increase in pressure will be that this constant pressure line will move, or it will shift in upward direction. So we are increasing the pressure, so this line has shifted to this, and finally when we are further increasing it, it will lead to this critical point. So all our supercritical power plants, basically power plants are of two types, subcritical, supercritical. So the supercritical power plants operate at a pressure more than the critical point pressure. This critical point parameters we will see in further slides. So quickly summarize some definitions which we had seen or we discussed in previous slides. So heat of vaporization, that is the amount of heat required to convert the liquid water completely into vapor. Then comes saturation temperature and saturation pressure. It is defined as the temperature at which vaporization takes place, that is saturation temperature, and the pressure corresponding to saturation temperature is your saturation pressure. The subcooled liquid is that liquid whose temperature on cooling becomes lower than the saturation temperature for the given pressure. So subcooled liquid's temperature will be always lesser than the saturation temperature at the given pressure. So in our earlier case of the water sample, the liquid is at 20 degrees centigrade at 1 atmospheric pressure. It means the liquid, the water sample what we have taken is in subcooled zone. So the same process is shown over the TS diagram. There is temperature entropy diagram, which is best for analysis of power station cycles. And any two thermodynamic parameters are sufficient to define the state of fluid as entropy, temperature, pressure, enthalpy. And the critical point parameters of water is that critical pressure is 22.09, or rather you can say 221 bar, that is 22.09 megapascals. Then temperature is 374.14 degrees centigrade, the parameters at this point, and specific volume will be 0.003155 meter cube per kg. So supercritical fluid is the fluid which is having pressure more than this critical pressure. So one more thing you can see, beyond critical pressure, suppose we are giving heat, so there won't be any significant phase change visible here. This liquid will suddenly flash into vapor without showing this wet zone or mixture phase. So this is the phase diagram, or that is PT diagram for water. The phase diagram gives idea about what phases are present at any given temperature and pressure. In the cases where we're looking the solid, liquid or vapor states of a pure substance. So here you can see if any substance at a given pressure and temperature is in this zone, that will be in the solid phase. If it is in this zone, it will be in liquid phase, and if it falls in this region, then it will be under vapor phase. So there are 2 points. There is T point marked here, and C is the critical point. This T is triple point. This is the point on a phase diagram at which the three states, that solid, liquid and vapor, coexist. And the critical point is defined as the point at which the substances is indistinguishable between liquid and gaseous phase. Now we will see the different type of steam, because this is important to understand here. So wet steam has the water content along with the gaseous steam, and for this reason the wet steam is at its boiling point. Any heat that is added to wet steam will be first used for boiling of remaining liquid water before the steam temperature can be raised. So till all the liquid portion of steam is not converted into steam, the water will be taking the latent heat of vaporization till full conversion of liquid portion into vapor portion. Then steam quality or dryness fraction that is associated with the wet steam is defined as the percentage gaseous content within the wet steam mixture, and this is an important parameter to define the exact thermodynamic state of the steam mixture. Steam with more liquid content is then considered to be of lesser quality. Then dry steam, this is this can be also taken as dry saturated steam. It is that steam where there is no liquid water content present. Since every water molecule is in vapor form, so here the dryness fraction or the quality of steam will be taken as 1, and the quality of dry steam will be said as 100%. So dry steam can be at or above the boiling point of the steam at given pressure. So if it is the dry steam is at saturation temperature, that is, then it will be signified as dry saturated steam. And if this temperature of dry steam is more than the saturation temperature, so that will be categorized as superheated steam. So superheated steam also has zero content and it is having more enthalpy. So steam is said to be superheated when it is heated above its boiling point temperature, and this way additional heat supplied is raised by gas molecules for temperature rise, or we can say the additional heat which is supplied is used to raise the temperature of gas molecules. Whenever dry steam at the boiling point is needed, a steam desuperheater can be used to bring down the steam temperature at around 3 degrees centigrade above the boiling point.